Section 9.6 Multiple Bonds. In the covalent bonds we've considered thus far, the electron density is concentrated along the line connecting the nuclei, the internuclear axis. In other words, the line joining the two nuclei passes through the middle of the overlap region. These bonds are called sigma bonds. The overlap of two s orbitals, as in hydrogen, the overlap of an s and p, as in hydrochloric acid, the overlap between two p orbitals, as in chlorine, and the overlap of a p and an sp orbital, as in beryllium fluoride, are all examples of sigma bonds. To describe multiple bonding, we must consider a second kind of bond that results from the overlap between two p orbitals oriented perpendicularly to the internuclear axis. This sideways overlap of p orbitals produces a pi bond. A pi bond is a covalent bond in which the overlap regions lie above and below the internuclear axis. Unlike a sigma bond, in a pi bond there are no probability of finding the electron on the internuclear axis because the pi orbitals in a pi bond overlap sideways rather than directly facing each other. The total overlap in a pi bond tends to be less than that of a sigma bond. Consequently, pi bonds are generally weaker than sigma bonds. In almost all cases, single bonds are sigma bonds. A double bond consists of one sigma bond and one pi bond, and a triple bond consists of one sigma bond and two pi bonds. To see how these ideas are used, consider ethylene, which possesses a carbon-carbon double bond. The bond angles in ethylene are all approximately 120 degrees, suggesting that each carbon atom uses sp2 hybrid orbitals to form sigma bonds with the other carbon and with the two hydrogen. Because carbon has 4 valence electrons, after sp2 hybridization, 1 electron in each of the carbon atoms remains in the unhybridized 2p orbital. The unhybridized 2p orbital is directed perpendicular to the plane of that contains the 3 sp2 hybrid orbitals. Each sp2 hybrid orbital on the carbon atom contains 1 electron. Figure 9.24 shows how the 4 carbon-hydrogen sigma bonds are formed by overlap of the sp2 hybrid orbitals on carbon with the 1s orbital of each hydrogen atom. We use 8 electrons to form these 4 electron pair bonds. The carbon-carbon sigma bond is formed by the overlap of 2 sp2 hybrid orbitals, 1 on each carbon atom, and requires 2 more electrons. Thus, 10 of the 12 valence electrons in the ethylene molecule are used to form 5 sigma bonds. The remaining 2 valence electrons reside in the unhybridized 2p orbitals, 1 electron in each carbon atom. These 2p orbitals can overlap with each other in a sideways fashion, as shown in figure 9.25. The resultant electron density is concentrated above and below the carbon-carbon bond axis, which means it is a pi bond. Thus, the carbon-carbon double bond in ethylene consists of 1 sigma bond, and 1 pi bond. Although we cannot experimentally observe a pi bond directly, as we can observe our positions of atoms, the structure of ethylene provides a long support for its presence. First, the carbon-carbon bond length in ethylene, 1.34 angstroms, is much shorter than in compounds with a carbon-carbon single bond, 1.54 angstroms, consistent with the presence of a stronger carbon-carbon double bond. Second, all 6 atoms in ethylene lie in the same plane. The 2p orbitals that make up the pi bonds can achieve a good overlap only when the 2 CH2 fragments lie in the same plane. If the pi bond were absent, there would be no reason for the 2 CH2 fragments of ethylene to lie on the same plane. Because pi bonds require the portions of a molecule to be planar, they can introduce rigidity into molecules. Triple bonds can also be explained by using hybrid orbitals. Acetylene, for example, is a linear molecule that contains a triple bond. The linear geometry suggests that each carbon atom uses sp hybrid orbitals to form sigma bonds with the other carbon and 1 hydrogen. Each carbon atom thus has 2 remaining unhybridized 2p orbitals at right angles to each other and the axis of the sp hybrid set. These p orbitals overlap to form a pair of pi bonds. Thus, the triple bond in acetylene consists of 1 sigma bond and 2 pi bonds. Although it's possible to make pi bonds from d orbitals, the only pi bonds we'll consider are the form for the overlap of p orbitals. These pi bonds can form only if unhybridized p orbitals are present on the bonded atoms. Therefore, only atoms having sp or sp2 hybridization can be involved in such pi bonding. Further, double and triple bonds, and hence pi bonds, are more common in molecules made up of small atoms from the second period, especially carbon, nitrogen, and oxygen. Larger atoms, such as sulfur, phosphorus, and silicon, form pi bonds less readily. Resonance structures, delocalization, and pi bonding. In the molecules we've discussed thus far in the section, the bonding electrons are localized. By this we mean that the sigma and pi bonds are associated together with the two atoms that form the bond. In many molecules, however, we cannot adequately describe the bonding as being entirely localized. This situation arises particularly in the molecules that have two or more resonance structure involving pi bonds. One molecule that cannot be described with localized pi bonds is benzene, which has two resonance structures. To describe the bonding in benzene using hybrid orbitals, we first choose a hybridization scheme consistent with the geometry of the molecule. Because each carbon is surrounded by three atoms at a 120-degree angle, the appropriate hybrid set is sp2. 6 localized carbon-carbon sigma bonds and 6 localized carbon-hydrogen sigma bonds are formed from the sp2 hybrid orbitals, as shown in figure 928. This leaves 2p orbital on each carbon that's oriented perpendicularly to the plane of the molecule. The situation is very much like the ethylene, except that now we have 6 carbon 2p orbitals arranged in a ring. Each of the unhybridized 2p orbitals is occupied by 1 electron, leaving a total of 6 electrons to be accounted for by pi bonding. We could envision using unhybridized 2p orbitals of benzene to form 3 localized pi bonds. As shown in figure 929, there are 2 equivalent ways to make these localized bonds, and each corresponds to one of the resonance structures of the molecule. A representation that reflects both resonance structures has the 6 pi bonds smeared out among the 6 carbon atoms, as shown in figure 929. Notice how the figure corresponds to the circle in a hexagon drawing that we often use to represent benzene. This model leads to the description of each carbon-carbon bond as having identical bond length that are between the length of carbon-carbon single and the length of a carbon-carbon double bond, consistent with the observed bond length of benzene. Because we cannot describe the pi bonds in benzene as individual electron bonds between neighboring atoms, we say that the pi bonds are delocalized among the 6 carbon atoms. Delocalization in the electrons in the pi bonds gives benzene a special stability, which we'll discuss in section 25.3. Delocalization of the pi bonds is also responsible for the color in many organic molecules. A final important point to remember about delocalized pi bonds is the constraint they place upon the geometry of a molecule. For optimum overlap of all unhybridized p orbitals, all of the atoms involved in the delocalized pi bonding network should lie in the same plane. This localization imparts a certain rigidity to the molecule that's absent in molecules containing only sigma bonds. If you take a course in organic chemistry, you'll find many examples of how electron delocalization influences the properties of organic molecules. General conclusions. On the basis of the examples we have seen, we can draw a few helpful conclusions for using the concept of hybrid orbitals to describe molecular structures. 1. Every pair of bonded atoms shares one or more pairs of electrons. The lines we draw in Lewis structures represents 2 electrons each. In every bond, at least one pair of electrons is localized in the space between the atoms in a sigma bond. The appropriate set of hybrid orbitals used to form the sigma bonds between an atom and its neighbors is determined by observed geometry of the molecule. The correlation between the set of hybrid orbitals and the geometry of the atom is given in Table 9.4. 2. The electrons in a sigma bond are localized in the region between 2 bonded atoms and do not make a significant contribution to the bonding between any other two atoms. 3. When atoms share more than one pair of electrons, one pair is used to form a sigma bond, the additional pairs form pi bonds. The centers of charge density in a pi bond lie above and below the internuclear axis. 4. Molecules with 2 or more resonance structures can have pi bonds that extend over 2 bonded atoms, Electrons in pi bonds that extend over more than two atoms are delocalized.